analysis of sway portal frames. You can also call it as analysis of portal frames with the sway. We already know that these portal frames, majorly we will see them as non-sway portal frames, and another one is sway portal frames. So non-sway as well as sway portal frames. Now you can see non-sway is nothing but when you consider a portal frame like this, due to the application of the loading, there will be no horizontal deformation. There is no horizontal deflection. Sway is nothing but a horizontal displacement of the member. So if a member is like this, and due to the application of loading, if it deforms like this, that will be considered as a sway problem. So this is considered as a sway structure. So this is, we call it as delta. So here in a portal frame, the sway occurs for different reasons. So the sway in a portal frame occurs in different reasons that we will see now. So here this is a non-sway portal frame. The analysis of non-sway portal frame is as similar to the analysis of a continuous beam. So you can first of all calculate the distribution factors at the joints, the fixed end moments. Now we can start analyzing the problem similar to that of our continuous beam. So that is, we have already done many of the problems regarding this. Now we will see in this class today how to analyze a sway portal frame. So before that, let us first of all discuss in how many ways or what are the conditions that prevail in a portal frame to get sway. That we will see now. So just keep heading. All of you just keep side heading. Reasons for side sway in portal frames. Reasons for side sway in portal frames. So what are the reasons that are affecting to get the side sway in a portal frame? So basically the first point is unsymmetrical loading. So when there is an unsymmetrical loading on the structure, that is nothing but eccentric loading, that will give sway in the structure. So just this is your structure, and eccentric loading is nothing but if the entire span is 5 meters, this is 2 meters, this is 3 meters. Now the loading, whatever that is acting on the beam element, it is acting eccentrically, so that will prevail side sway in portal frames. That is one type of loading, that is the condition for side sway in portal frame. Now coming to the second one, different moment of inertia. Different moment of inertia of column members. So when you consider this is a portal frame, here the moment of inertia of this section is 2I and this is I, that will also lead to sway in the structure. So different moment of inertia, in other words, you can also say non-uniform sections. So you can also call it as non-uniform sections. So that is the dimensions of the section when they are different. That will also for the columns, particularly only for the columns. The sway is particularly for columns only. That will also affect the sway, side sway in portal frames. And obviously the third one is horizontal loading on the columns. Horizontal loading on columns. So this horizontal loading on the columns of the portal frame. So for example, your portal frame, when it is subjected to a horizontal loading like this, that will also affect a side sway in the structure. A side sway in the structure. Now the next one is settlement of the supports of the frame. Settlement of the supports of the frame. So for example, your frame is like this, which is having a symmetrical loading on the beam. But what happened is some support, it got sunk like this. Support got deflection like this. Support settlement delta. That will also lead to a settlement of the supports. That will also lead to side sway in the portal frame. That is also another condition. Unsymmetrical outline of the portal frame. Unsymmetrical outline of the portal frame, that is the lengths are different here. Here this is also lead to, this is L1, this is L2. So whereas the lengths are different, that will also affect side sway in the portal frame. Analyze the given portal frame. With moment distribution method. Now, in this one, you can observe this. There is no horizontal loading. Here, this is 2i 4 meters. This is 2i 4 meters. Moment of inertia of the two columns is uniform. Lengths are uniform. But the eccentric loading is acting on the beam. This eccentric loading will create sway. Okay. So the sway will be like this. I'm just drawing the elastic curve. So this is delta. This is delta. So this sway analysis we will do in two parts. One is we will do non-sway analysis. In the second step, we will do sway analysis. Understand this problem properly. So first of all, first write down the fixed end moments. Okay, now tell me what is MFAB? What is the value of MFAB?
0, sir.
Yes. MFAB is 0. Why? Because there is no loading. That's why MFAB is 0. What about MFBA? That is also 0 as there is no loading. MFBC. What is the value of MFBC?
Minus WAB square by L square.
Minus WAB square
AB square.
by L square. AB, BA, CD, DC. Yes, the moments at AB, BA, CD, DC are 0. MFBC is nothing but minus 60 into 2 into 4 square by 6 square. After this, we need to go with the distribution factors. Distribution factor at BA, distribution factor at BC. Why? Because now I am writing it joint B. So here the joint B is nothing but this is the point BA, BC. So when you are writing it BA, now you can see this the relative stiffness of the member is nothing but in this point KBA is nothing but 2I by 4. There is the far end is fixed. That's why this is 2I by 4. For BC, KBC is nothing but the relative stiffness of the member is with respect to B. The C is a continuous support. That's why this is I by 6. KCD is nothing but with respect to C, that is far end is D is fixed. So this is 2I by 4. We need to understand the relative stiffness of the members. So DFBA is nothing but KBA by KBA plus KBC. Darpan, are you there? Darpan. Vishnu 186. One 187, 96, 187. I want the response of the people. Yes. Right, Vishnu. Okay. So in this DFBC is nothing but KBC by KBA plus KBC. Now write down the values. KBA is this is 2I by 4 by 2I by 4 plus I by 6. This is I by 6 by 2I by 4 plus I by 6. 1. Now at joint C, DF CB, DF CD, KBC, sorry, KCB, KCB plus KCD, KCD by KCB plus KCD. Now in this one, what is KCB? It is equal to KBC only, which is I by 6 by I by 6 plus 2I by 4. 2i by 4 by I by 6 plus 2i by 4, which is this one will be 1 by 4, this one will be 3 by 4. In this problem, what we will do is, this is a sway condition. Why? Because the loading is eccentric. That's why this is sway problem. So to do this sway problem, what we will do is, first of all, we will do non-sway analysis, then we will do sway analysis. So first, in the first step, we will calculate fixed end moments. In the second step, I will calculate the distribution factors. Now I will go with the non-sway analysis. So keep side heading non-sway analysis. Keep side heading non-sway analysis. So this is your beam, sorry, portal frame. Which is 4 meters, which is 4 meters here. A loading is acting here, which is 60 kilonewton. This is B, this is C, this is A, this is D. Now in this condition, what I will write down is joint member distribution factors fixed ends member BA, member BC, member CD, member DC, sorry, member CB, member CD, member DC. Coming to distribution factors, this is AB is one only, but we have joint B. BA is there, BC is there. What is the value of BA? The value of BA is 3 by 4, which is 0.75. BC is 0.25. CB is 0.25. CD is 0.75. And DC is one only actually, you need not write down that one. So coming to the fixed end moments. So the fixed end moments are for AB, that is 0, BA 0, BC. What is BC value? So due to this loading, we got it as a minus 53.33. So that is MFBC is minus 53.33 kilonewton meter. Whereas coming to CB, plus 26.67 kilonewton meter, MCD 0, MBC 0. We are doing non-sway analysis. I am doing only, that is forgetting about the sway. In the normal manner, I am calculating the balancing. So to balance this, you know that whenever I am considering a joint, summation of the moments at a particular joint is equal to 0. So summation of a moments at a particular joint is equal to 0 means MBA plus MBC should be equal to, similar way, MCB plus MCD is equal to 0. Just understand. So this is your portal frame. Summation of the moments at a particular joint is equal to 0. But here the difference between them is minus 53.33. So the difference is minus 53.33. You take the opposite sign, plus 53.33. And that is to be distributed with the distribution factors for BA as well as BC. So balance here, you have to balance both the members BA as well as BC simultaneously. So balance B and C simultaneously, you need to balance. So when you would like to balance B and C simultaneously, this is the difference between, that is, if you add both, the value is minus 53.33, and you need to consider opposite sign, which is plus 53.33. Plus 53.33 multiplied with What is the value? Distribution factor 0.75. This is plus 53.33 into 0.25. Whereas in this condition, CB, for this CB plus 26.67, that is positive value, you need to consider minus 26.67 into 0.25 minus 26.67 into 0.75. So tell me the value plus 53.33 into 0.75.
40, sir. 39.9.
40. So you need to understand from where to where the carryover moments will be there. Just see this once again. Carryover moments. So for this, which one is nearer? For BA, there is the far end is nothing but AB. The far end is for AB. Why? Because you just, if you go to the diagram, you will understand. You are writing BA, so the far end is AB. If you write down for BC, the far end is CB. If you write down for CD, the far end is DC. So the carryover moments will be there here from BA to AB. So half of the moment will be carried over. So this is 40 by 2. Then from BC, the far end is nothing but CB. So from 13.33, as you have balanced, this is 13.33 by 2. Similar way for CB, the far end is BC, minus 6.67 by 2. And for CD, the far end is DC, minus 20 by 2. So now continue for this, write down the net moments. And now if you observe 40 minus 43.33, the value is minus 3.33. You need to go with plus 3.33. That's it, right?
Yes, sir.
So plus 3.33 into 0.75. What is the value? Once again, check this one. Joint conditions, whether they have satisfied or not. At a particular joint B, this is joint B. The values are, this is BA, this is BC, this is CB, this is CD. So summation of the joints in a particular joint is to be equal to 0. 25.415 minus 25, which should be equal to 0. But here the difference is there. That's why once again you have to balance it. When you balance once again, so it is balance B and C. When you balance this, now what is there? What is the difference between these two? If you add both, 42.5 minus 43.33, the value is minus 0.83. So minus 0.83 is the difference, is the value which is added. Now take plus 0.83, opposite sign, plus 0.83 multiplied with 0.75, plus 0.83 multiplied with 0.25. Now in this case, 25.415 minus 25, which is 0.415, is the remaining difference. You do minus 0.415 into 0.25 minus 0.415 into 0.75. So then carry out the next once again. So here the carrier elements are from here to here, from here to here, from here to here, from here to here. CB is 26.225. What is the value, Suma? 26.225. Final value you are saying, or only the carrier elements you are saying? Are you saying the previous step net moments or the final step, next further step you are saying? plus 26.225 we have written. What is that value from where? Okay, now let me write down the carrier moments. Plus 0.83 into 0.75. What is the value here? Plus 0.83 into 0.75.
0.625.
0.625. So this is 0.83 into 0.25. 0.2. I can write down this as a 0.62. I will write down here, and next value will be 0.21. This is 0.21. So in the coming way, 0.415 into 0.25. 10.38.
0.103.
0.104
103.
I will write down. Why? Because it is 0.10375. I can write down it as 0.104, which is negative. This is minus, what is the remaining value?
0.311.
0.311. So they are to be carried over. So this is 0.62 by 2, and this is minus 0.104 by 2. This is 0.21 by 2, and this is minus 0.311 by 2. Now write down the moments. (21.25 by 0.62). Plus we go there. Plus 0.62 by 2. Okay. So the moments are obtained. Okay, if you do once again, this error can also be minimized. However, that is sufficient. So I will write down this as these are non-sway moments. I will write down this as m dash ab is equal to 21.56 kilonewton meter. M dash BA is equal to, I am not writing final moments. Why? Because these are non-sway moments only. So these are non-sway moments. They are not sway moments. M dash BC is equal to minus 43.17 kilonewton meter. M dash CB is equal to plus 25.416 kilonewton meter. M dash CD is equal to minus 25.311 kilonewton meter. M dash DC is equal to minus 12.66 kilonewton meter. You write down them as non-sway moments. So, till now what we have done is, without considering the sway effect, we have calculated the moments. Nowhere we have introduced the sway value. Simply, whatever the problem we have done with respect to without any deflection, in a similar manner, we completed this problem. Now, what we will do is, we will do sway analysis. This is, remember these values, these are considered as non-sway moments. Now we need to go with the sway moments. So just I am writing here sway analysis. So here in the sway analysis, what I will do is, here I will prepare a tabular form, which is, first of all, we'll write down joint, we'll write down member, then fixed end moment, then here these things are first of all to be written. So remember AB, BA, BC, CB, CD, DC. This is joint A, joint B, joint C, joint D. Now remember this. Where the sway will occur, either in the beams or the columns? I want your response. Where the sway will occur?
Columns, sir.
In the columns. So what are
Columns beam lo
that means we will not get any sway only if you observe this is your column. This column is when a horizontal force or a sway condition is happening, it will displace like this. So what are the corresponding sway moments which are considered as that is the sway will occur in the column moments. So AB is a column moment, BA is a column moment. These two are considered the column moments for AB, whereas CD as well as DC, they are considered as column moments. This is very, very important. Remember this point. That means here we are considering column moments. So here we have to assume the fixed end moments here. So first of all, we have done the sway moments, we have done non-sway moments. Here in this one, we need to assume fixed end moments values. How do we assume these fixed end moments values? Just let me explain you here. Here, see this one. In the sway analysis, first of all, I forgot to write down the distribution factors. Here we need to write down the distribution factors also. So here this column I am just this row I am giving for distribution factors. So for the distribution factor, what is the distribution factor for BA? This will be as same as our previous one. The distribution factor is nothing but 0.75, 0.25, 0.25, 0.75. So bring the same thing here. Okay, now here according to this we have to assume fixed end moments. So what I am assuming is fixed end moments. So the fixed end moments are assumed like some numerical value I have to assume here. So to assume this, we have to follow the deflection according to the length of the member. We have to assume the ratios are to be assumed in such a manner that they are following the deflection profile. Now see here, what is the delta here? The both AB as well as CD, the lengths are same only. This is 4 meters, this is 4 meters. Both the lengths are same. If this is delta, just see this one. You can simply rotate it. AB, you can rotate it. I'm just rotating like this. This is A, this is B. It can get a deflection like this, which is delta. So if that is the condition for a fixed beam, we know what is the fixed end moment when this support is sinking, delta minus 6 EI delta by L square. Yes or not?
Yes, sir, correct.
So when a fixed beam support is there, when its support is sinking, then the value is minus 6 EI delta by L square. Right. So This is minus 68 delta by L square. So corresponding to that, similar way here also in the other condition, what is for CD? This is also length is same for both the conditions. So if I write down MBA by MCD, sorry, here just to make a correction. This is B, this is C. If I write down MBA, what is the value of MBA? BA minus 6 EI delta by L square. What is the length? 4 square. Whereas this is D, this is C. The support is sinking like this. I'm just rotating this portion. So this is MCD is once again minus 60 EI delta by L square. So the ratio of MBA by MCD, that is MBA by MCD, is nothing but 1 only. So you have to assume the moments in such a manner that you see this. I'm just assuming one numerical value. This is minus 100, minus 100. This is BC is a beam moment. I am not writing the sway moments here. Why? Because BC doesn't undergo any sway condition. CB is also beam moment, which is not a column moment. That's why I will not write down minus 100, minus 100. Understand here why I have written like this. Just you can take this also 10 also, no problem. This is a numerical value, that's it. It is a factor and it will be adjusted in the further steps. So you can assume 50 also, you can assume 10 also, you can assume 20 also, you can assume 30 also. Any value you can assume, and this will be adjusted. How it is adjusted and how you are assuming all the values same here, minus 100, minus 100, minus 100, minus 100. These are the column moments: MAB, MBA, MBC, MBA, MAB, MCD, MDC. Here, as the lengths are uniform, as the lengths are 4 meters, you have, and the deflection delta is same for both the conditions. This is also delta. So that is the sinking of the support, due to sinking of the support or due to the sway. The moment is, sway moment is 68 delta by L square, and both are same. MBA as well as MCD both are same. That's why the ratio of the moments is 1. If the ratio of the moments is 1, then assume it as equally. So that's why we are assuming both as same, minus 100, minus 100, and CD also minus 100, DC also minus 100. But here, after writing the fixed moments, you have to balance it. Which one you have to balance? You have to balance B and C. Why I should balance B and C? At a particular joint, BA and BC should be equal, but here this is the difference is minus 100. Here the difference is minus 100. That's why I have to balance B and C. How to balance it? Minus 100 is there, take plus 100 into 0.75, 100 into 0.25. This is 100 into 0.25, 100 into 0.75. To simply multiply easily, that's why I have taken as 100. If I take 20 or 30, I require calculator. Here this is 100 into 0.75. Easily I can write down as 75. This is as 25. This is as 25. This is as 75. Now carry over moment is there. So what is the carry over moment from here to here? 75 by 2. For 25, 25 by 2. Here, 25 by 2. Here. Now write down the end moments, that is moments. Minus 100, 75 by 2. What is the value here? Minus 62.5. Minus 100 plus 75 minus 25. 25 by 2. 37.5. 37.5 minus 25 minus 62.5. Check the values whether they are correct or not. Are they correct? Are you there to follow the class or not? Are you there? So can I continue further? Now, here the moments are calculated. Now we go for balance B and C. So to balance B and C, now check this one. This is minus 25. This is 37.5. So minus 25 plus 37.5. The value is 12.5. So this 12.5 you take it as negative 12.5 into 0.75 minus 12.5 into 0.25. This is 37.5 minus 25. Similarly, this is also minus 12.5 into 0.25 minus 12.5 into 0.75. What is the value here? Minus 12.5 into 0.75. What is the value? The carrier moments. So after this, write down the carrier moments. Is minus 9.375 by 2. This is minus 3.125 by 2, minus 3.125 by 2, minus 9.375 by 2. Now write down the moments. If any values are wrong, let me know. Once again, balance B and C. The values are not equal, but they are closer compared to the previous step. They are coming closer. The difference is being reduced. So minus 34.38, 32.81. That is minus 1.57. Consider plus 1.57, which is 1.57 into 0.25. This is 1.57 into 0.25. 1.57 into 0.75. Now write down the carrier moments. 1.18 by 2, 0.39 by 2, 0.39 by 2, 1.18 by 2. So write down the moments. As of now, actually the values are not closure. Once again, you have to do iteration. But however, I am stopping here. Why? Because we have done around 3 times. Actually, we have to do another 1 time to bring the values much closer. So, due to the lack of the time, I am continuing further. Why? Because these are sway moments. These are considered written as m double dash AB, which is nothing but minus 656.6 kilonewton meter. M double dash BA is equal to minus 33.2 kilonewton meter. M double dash BC is equal to plus 33.39 kilonewton meter. M double dash CB is equal to plus 33.39 kilonewton meter. M double dash CD is equal to minus 3.2 kilonewton meter. M double dash DC is equal to 6 kilonewton meter. So these are called as sway moments. But here, understand one point. These sway moments, 66.6 kilonewton meter, how you arrive this value? By assuming one value here, which is 100. But our 100 value, whatever you have assumed, that is a assumed value. So what I will write on this here, that is an assumed value. This is not whatever the moments you got. These are the with respect to assumed 100 value, you got these values. So while writing total, writing down the total moments. So total moments, the formula is total moments is equal to non-sway moments plus x into sway moments. Instead of x, I will write on k, on factor k. K into sway moments. Why I am multiplying with the k is nothing but it is a factor which edges our assumed value. We have assumed 100, but to make it actual value, I am considering a factor which is k. Now, total moments are nothing but non-sway moments plus k into sway moments. Now, here our total moments MAB is equal to M dash AB plus K into M double dash AB. So what is M dash AB value? Have you got this M dash AB 21.56? So 21.56 minus K into here plus K into minus 66.6, which is 21.56 minus 66.6 into K. This is equation number 1. In the sway problems, what I have done in the first one, I have assumed the problem as a non-sway condition. The non-sway moments are calculated and sway moments are analyzed separately, but these sway moments are analyzed according to the ratio of the sway moments. The sway moments are MAB is minus 68 delta by L square. MBA is minus 68 delta by L square. Length of the members is equal. That's why we assumed the ratios of the moments as in the same factor. That's why I assumed them as 100, 100, 100. Now after that, the sway moments are calculated. But these sway moments, they are not the actual values. They are multiplied with a factor k. Why? Because as they are assumed, we should get exact value. So here the total moments are nothing but sway moments plus some factor multiplied with sway moments. Non-sway moment plus factor into sway moments. Similarly, MBA is equal to M dash BA plus K into M double dash into BA. So which is, can anyone of you tell me the values for 43.12? Plus K into, what is the value here? We got. What is the moment we got here? Oh, sorry, minus 33.2. And the value here it is 43.12 minus 33.2 into K. So keep that equation number 2. Now continue further. MBC is nothing but, directly writing down, MBC is M dash BC minus 43.17 minus 43.17. MBC, M double dash BC is 33.3739 plus 33.39 into K. So this is equation number 3. MBC, MCB is equal to, so MCB plus 25.416 plus 25.416 we are writing for MBC plus 33.39 into K. We are writing for MCB, that is plus 30.39 into K. This is equation number 4. Now, writing down for roll number 118, 19 series, Shivkumara. Yes, are you following Shiva? Right. You should note down the things. MCD is equal to M dash CD. That is non-sway moment plus. What is the non-sway moment? M dash CD is minus 25.311 minus 25.311 plus this one value minus 33.2 minus 33.2 into K minus 33.2 into K. This is 5. Now MDC is equal to non-sway moment minus 12.66 minus 12.66 minus 66.6 into K. This is equation number 6. So overall, we got the equations, total moments we got, but is a value of K. So to get this one, we will go with the help of horizontal condition. Horizontal condition. With the horizontal condition is to be written. Okay, Rohit. Now the horizontal condition. Write down. So in this horizontal condition, we have to consider a column AB. So this is A, this is B. Column AB will be considered. For the horizontal conditions, only columns are considered. So we are assuming that this is MBA, clockwise movement. This is MAB, clockwise movement. The length of the movement is 4 meters. So the sway is happening in the right side, so the reaction will be there in the left side. So the horizontal conditions we are writing like this. Now, taking moment about B is equal to 0. You take moments about B is equal to 0 here. So when you take moments about B is equal to 0, so here just clockwise moments are positive. HA into 4 plus MAB plus MBA is equal to 0. So HA is equal to minus of MAB plus MBA by 4. HA is equal to minus of MBAB plus MBA by 4. So this is one horizontal reaction for a column AB. Similar way, consider column C, D. So this is horizontal force HD. This is horizontal force HC. Moment is MCD. This moment is MDC. So sigma m about C is equal to 0. We have done this type of problems in the stroke deflection method. Horizontal shear conditions we have considered. HD into 4, that is force into distance 4 meters, plus MCD, that is clockwise moment is positive. You are considering moment about point C is equal to 0. HD into 4 plus MCD into MCD plus MDC is equal to 0. So HD is equal to minus of MCD plus MDC by 4. That is, we have considered the free body diagram of column AB, FBD of column AB, free body diagram of column CD. So with this, we got the horizontal reactions HA as well as HAD in terms of moments MAB, MBA, like that we calculated. Now, we do horizontal shear condition. In this, draw the free body diagram for the entire frame. This is HA, this is HD, and in this one, there is no horizontal force. I am writing only the horizontal forces only. There is only vertical force acting on the beam, which is not considered as a horizontal force. You can take it as sigma Fx is equal to 0. There is no other force acting on the particular portal frame. So HA plus HD is equal to 0. So this is considered as your equation number 7. This is equation number 8. This is equation number 9. Now substitute HA and HD values in this equation. Substitute HA and HD values in this equation. Minus of MAB plus MBA by 4 minus of MCD plus MDC by 4 is equal to 0. Here 1 minus 1 by 4 can be taken as common, and you will get, and if it is sent to the right side, then it will be 0 only. 4 into 0, 0 only. MAB plus MBA plus MCD plus MDC is equal to 0. So these are the MAB, MBA, MCD, MDC is equal to 0. This is equation number 10. Simplify this and tell me the value of K. This 0.134 is to be substituted in all the 6 equations to get the total end moments. To get the total end moments, we have to get the final end moments. Now substitute 0.134, that is a factor. So all the equations we have to get MAB is nothing but 21.56 minus 66.6 into 0.134. So okay. So the total moments are calculated here. The total moments MAB, MBA, MBC, MCB, MCD, MDC, all the 6 moments are written here after calculating the factor K. Now we have to draw shear force diagram as well as bending moment diagram. We have to draw shear force diagram as well as bending moment diagram. So first of all, let me recall our beam with loading. So a 60 kilonewton load is acting on the beam. This is 2 meters, this is 4 meters. A, B, C, D doesn't have any loading. So now draw Sfd and Pmd. So the beam is the portal frame. The given portal frame is like this. Four meters. This is 2y. 4 meters. This is 2y. A load of 60 kilonewtons is acting. This is 2 meters. This is 4 meters. A, B, C, D. Now, to draw SFD as well as BMD, individually we have to consider columns as well as beams separately. So if you go here, now first AB, so in this AB, the reactions are there here. Similarly, here these are the horizontal forces are there, HA, and this is HB. Now, in this, the moments are there. So, what is the direction of the moment? So you have to consider clockwise moment positive. So that's why this is giving a clockwise moment 12.63 kilonewton meter. MAB is 12.63 kilonewton meter. Similar way, MBA is acting, which is 38.67. That's it. On column AB, there are no other forces. Only the two moments are acting at the ends. Now, considering the horizontal condition, this horizontal forces sigma fx is equal to 0 plus HA. No, you can't consider plus. Why? Because it is going in the negative x-axis. Minus HA minus HB is equal to 0. That means HA is equal to minus HB. Sigma fx is equal to 0. That is HA is equal to minus HB. Taking moments about B is equal to 0. Taking moments about B is equal to 0. Now, can anyone of you tell me what is the moment here we have to consider? Plus 12.63 is clockwise moment. Plus 38.67 is also clockwise moment. But similar way, plus HA into 4 is equal to 0. This is 4 meters distance. So that is also clockwise. Plus 12.63 plus 38.67 plus HA into 4 is equal to 0. Now tell me what is the value of HA?
12.825.
Minus 12.825 kilonewtons. Check everyone. Is it correct or not? Then HB will become minus of HA, which is 12.825 kilonewtons. So the shear force diagram, first of all, this is HA and HB are calculated, horizontal forces are calculated. Now we will go to free body diagram of BC. BC portion we will go, this is B portion, this is C portion. Now here, a load of 60 kilonewtons is acting. A load of 60 kilonewtons, this is 2 meters, this is 4 meters. Now you can consider this is RB, this is RC. So in this one, we have to give the moments also. So MBC as well as MCB are to be mentioned, which is minus 38.69. This is plus 29.89. Minus 38.69 is nothing but negative sign indicates anti-clockwise direction. So this is anti-clockwise 38.69. This is clockwise moment. Just remember, this is clockwise positive and this is anti-clockwise. Sorry, this is clockwise positive only and this is giving you negative anti-clockwise. So which is 28.89 kilonewton meter. So writing down sigma F5 is equal to 0, RB plus RC is equal to 60. Taking moment about B is equal to 0, minus RC into 6, the distance is 6 meters, plus 60 into 2, plus 28.89, which is clockwise moment, minus 38.69, anti-clockwise moment is equal to 0. Just write down the taking moment about B is equal to 0, that's it. We got RC and RB values. Now go to the CD. Write down column CD, the flipper diagram for column CD. So this is C, this is D. Now here, mention the forces. In this direction, HD is there, horizontal force. This is HC is there. Now in this one, there is no external loading, but here the moments are there, minus 29.75, minus 21.58, minus 29.75, which is anti-clockwise. So this will come like this. MCD 29 point, what is the value? 29.75. And this is also anti-clockwise 21.58. Now taking sigma fx is equal to 0, minus hc minus hd is equal to 0. That implies hc is equal to minus hd. Taking moment about c is equal to 0, plus hd into 4, the distance is 4 meters, plus hd into 4, minus 29.75, minus 21.58. Why I am writing negative is they are anti-clockwise moments is equal to 0. So in this, so now we will draw the shear force diagram with the obtained values. First of all, shear force diagram. So while drawing the shear force diagram, I am drawing the reference in the portal frame also. So in this, first of all, I'm just drawn the outline diagram, baseline. Now if you go HA and just you can see HB portion, sorry, AB portion. If you understand AB portion, it is obtained as a minus 12.825. HA is minus 12.825. HB is 12.825. Just see this. This is your portion. Just you can make it horizontal like this. This point is A, this point is B. This is HA like this, HB like this. But HA is coming negative. That means the loading is coming in this direction like this. We know that left side upward is positive, left side upward is the left side downward is negative. Similar way, here this is HB is positive, that means it is the direction is same. So right side upward is negative, right side downward is positive. So just what I have done is I have turned the beam, that's it. Nothing I have done. So if I do like this you get it as 12.825. This one, this is negative portion. Here also, just for the color changes, I'm just changing the color to, this is 12.825 negative. And there is no loading in between that AB portion. There is no loading, hence it is constant. Negative. .825 kilonewtons. This is for A, this is for B. It's already a beam. And we got already RC as well as RB. RC is 18.36, RB is 41.64. So left side RB is going positive only, which means that it is going in the upward direction. Left side upward is positive, which is 41.64. So this is 41.64. So 41.64, just for the thing, I can change the color for better understanding here. This is 41.64. And you know that there is no load here. This is constant. This is a line. And it is constant until 2 meters. And at 2 meters, a load of 60 kilonewtons is acting, which is minus 60. So it will go down. And the value of RC is 18.36, I think. 18.36. So 41.64 minus 60, which is 18.36. And this is diagram for beam. This is a diagram for beam. Now, turn, just we have, what we have done is, for our better understanding, we have made, this is BC, this portion is A, just make it as a horizontal. Now this is CD. Now you go to CD beam. So this is like this is C, this is D. HC is shown like this, which is coming downward direction. HD is also coming like this. Now HC is given as minus 12.83. That means here you have to change the sign, which is in the opposite direction, minus 12.83. Left side upward is positive, and here you will get it as once again I will change another direction. Okay, and this is positive, so this is the line, baseline, and this is 12.825 only, that is at 83. This is positive. In between there is no change in the load, which is 12.83 kilonewtons. And here the value is 18.36 kilonewtons. So this is SFD. This is our SFD diagram. Now we have to draw bending moment diagram for this. So bending moment diagram we have to draw here. So to draw bending moment diagram, so already our reference bottle frame is there here. AB is not subjected to any positive bending moment as it is having only so just here the line, the reference line I am drawing. This is A, this is B. Now in this, if you understand, what is the direction of the moments that are acting on AB column? Just go to AB column once. Just understand here. Now if you understand, this is a clockwise moment acting. This clockwise moment, it is coming like this in this direction. And this is also a clockwise moment acting like this. This moment, 12.63 kilonewton meter, is trying to push in this direction. So when it tries, just see this one, this is your AB. A clockwise moment, when it is tries to push, the moment will be in this direction. Whereas here another one, it is a moment is trying to push here, it is going in this direction. So here the value is 38.67, here the value is 12.63. This is the way how we will write down the moments. Both are positive, please don't give the positive sign. Here according to the sign, positive sign, they are trying to push the column like this. So this is this is 38.67. This is 12.63. So join them like this. This is BMD. Now whereas coming to BC, so for the BC portion, so at BC the support moments are MBC is nothing but, what is the value of MBC here? 38.69, 28.89. 38.69, 28.89, I think. Let me check once again. That is 28.89, right. Now these are nothing but support moments which are negative. But along with this, we have positive moments are there due to loading. As 60 kilonewtons is acting, so this 60 into, for example, a simple supported beam with 60 kilonewtons loading, it will produce a maximum moment of WAB by L. And the value is 60 into 2 into 4 by 6, which is 80 kilonewton meter. Just check it.
Yes, sir.
So a 80 kilonewton load is giving you a positive moment. A kilometer bending moment is positive bending moment. So this portion is negative, this portion is positive, this portion is negative. So the hatched portion, whatever I am hatching, this is the portion which is the bending moment diagram for the beam. Slightly it is typical, try to understand. With practice you will understand it. Now this is BC portion is completed. Now we have to go for CD portion. For CD portion, now once again go to the column and understand the moment, direction of the moments. So both are anti-clockwise and the value is 29.75, 21.58. So just see this one. This moment is trying to push in this way. This moment is trying to push in this way. So 21.58. This is 28.89, I think. What is the value here? 29.75. So this is the diagram. Don't use sign convention here for the columns, and that is bending moment diagram here. So here the sign convention how we are giving according to the movement direction. So how it is applied on the column, according to that the bending moment diagrams are drawn. So be careful while mentioning the bending moment diagrams. So if this is completed, now we'll go to the another problem. So this is the hatched question, you have to hatch it.